Please welcome Mark to S4's Stage 2.
Thank you all for coming. Look forward to this conversation, and I intend to leave some time at the end for any questions that people might have. I'm really going to kind of get pretty deep in control systems today and things that are down there that are familiar to control engineers, things they're kind of aware of and they manage today, but really simple things you can do inside the configuration of a control system that can cause really significant problems. So I think about the good old days when, if you will, OT was collateral damage of IT security things, people trying to steal data, and they ran into control systems, they got down there, they found this weird stuff, and they couldn't make money at it. That days have changed. It's very clear through documented successful attacks that the bad guys, if you will, are learning about OT. They're buying systems, they're investigating, they're looking for weaknesses that they can exploit, whether it be through communications or other things like that. Kind of the third leg of the triangle, if you really want to cause physical damage, is understanding of the process underneath. What I mean by that is that if I line up a traditional IT hacker that can get me in, and I know someone that knows that particular control system, they know that DCS or the PLC, and then you line up, if I'm at a refinery, a chemical engineer who knows refining processes, or polymers processes, or offshore production. You line those three things up, those three levels of expertise, really big physical problems can take place. And if we think that's not happening, I think we're kidding ourselves. And that's really what we're trying to do. Ultimately, the way that you're going to manifest change to cause physical damage is changing the configuration of OT. That's where the problems, you go from a digital event to a physical event, ultimately is by changing the configuration. So, where do we get this data from? Well, PAS has been a company doing controls work for over 20 years, really about safety and reliability as well as security. We have a lot of control systems under management of our solutions. In this recent study, we looked at data from 10,000 plus industrial endpoints, PLCs, and safety systems, distributed control systems, found lots and lots of vulnerabilities, primarily from the industries we serve the most, oil and gas, refining, call it the heavy processing industries, mining, metals, all those things where we do most of our work. Surprise, surprise, by far the most vulnerabilities out in the OT world are by Microsoft. I mean, no one's surprised by that, no big revelation there. Nothing else even comes close. As we went from very closed systems to more open systems, and Microsoft was introduced to the environment, it created new things that we had to manage. But there are vulnerabilities out there that have been introduced by the automation vendors themselves. And I'm not going to go into these in all detail, but these are known vulnerabilities as published by the National Vulnerability Database. And looking at that data set that I just spoke about, I can tell you this, and these slides will be available so you can get them all. But if you operate in the industries that I mentioned, and you have these vendors, which you probably do, Honeywell, Rockwell, and Yokogawa, those vulnerabilities will exist. And the remediation is known. A lot of these are DLL files, they're not hard to remediate, but I can promise you they're going to be out there in your environment that have to be addressed. But I want to get some things a bit more interesting, a little bit more. So if I've got access, what can I do? And I'm really going to be talking about, and the word vulnerability might not be the right word. It might be weaknesses or flaws, but basically things that I can do in OT configuration that's really easy to do. So before we get into that, let's talk about the construct of OT configuration. And there's three main elements. You have a control function. A control function is basically compiled code and a bunch of libraries that get shipped with whatever automation system you buy, a DCS, a PLC, etc., to do certain things. And you pick from the library, and then you configure it for your process, and then you put it online. So an example is a flow controller. And in that thing, there's things like model equations and data acquisition, error handling, alarms, all kinds of other things. And you configure things called parameters to match your process to make it work. So you're not writing code per se, you're configuring. The next layer are applications. Applications can be embedded inside the system. So things like AMCL, SFC, those are specific programming languages that exist specifically inside control systems. And then third-party things that interact with the control system, advanced process control optimizers that read things and then tell those control functions to do different things. Now, those applications can be configuration, they can also be code. The last layer is the HMI, or the graphics, and this is where human beings interact with the control system, whether it be operators or engineers, to see what's going on inside of there, get information, and perhaps tell it to do something different. And we're going to look at various things that are out there in the industry that could be concerning. Other big difference here, in the DCS, or distributed control system world, which is the dominant system for heavy processing industries to control the main part of the process, once you've done the initial implementation of the DCS, and chances are it was 15, 20 years ago, most changes are done online. You go to the system, you go to an engineering console, you say, I want to change this setting here, or add this here, do different things, and you do it live on the controller. PLC world's a little bit different. For the most part, changes made to configuration is done through a configuration program that is then basically compiled and then downloaded. You can see it in more custom language, and then it basically turns into the ones and zeros that gets downloaded into the actual PLC itself. So big difference between those two that does have a big impact on how you manage configuration. So we're going to get into specifics now, things that are out there. And I've organized this in two different ways. Ubiquitous weaknesses, and for this conversation, I'm going to call them weaknesses. They're everywhere. It's a characteristic in virtually all control systems that you need to be aware of that are easy to change that can cause big problems. The second thing are unique weaknesses. In one case, it's truly a vulnerability that exists out there, but the rest really can be classified as weaknesses. And these are very specific to an OT manufacturer and model. But here's an important thing. I'm not going to give you enough information to know exactly which manufacturer and model. I don't want to give the wrong people a head start on this. A control engineer, if he knows particular systems, might chuckle during this presentation because they knows about this thing. And if you want more information later, happy to talk to you offline and give you more information about some of these things and be more specific about it. But I have deliberately obscured some of the information so that, since this is being published, so that people can't do anything about it. So let's start one with it is ubiquitous. I call this one the reverse. That control function we talked about earlier has a parameter characteristic called the output characteristic. And this is basically what it means. If, say, I have a flow controller, and I'm an operator, and I say, I want the flow to be equal to 100, and the current process value is 90. Basically, what the control function does, it says, oh, get data, solve an equation, see an error, tell the valve to do something to try and get the process up to my desired value. That's the basic thing of what a controller does. There is a setting inside of there, again called the output characteristic, that is binary. It's either direct or indirect. And direct means when I do this, give it more air or electricity or whatever, and open the valve more to get the process where I want it to be. Indirect will basically send the opposite signal to the device in the field. So what does that mean? Basically, I can change that one setting, and if that valve is supposed to do this, it's going to do the exact opposite. And if I do that for a whole bunch of valves, you can imagine the production problem that I'm going to cause. And even worse, if that particular valve is associated with a safety function, and I change that setting and just leave it be, at the time when that valve, say, is supposed to close in an emergency, it's going to do the exact opposite. There's lots of ways that I can actually change that function through bulk, a couple devices, a lot of different things. And I'm going to be on the sponsor stage at 3:45 this afternoon. And if you want to come learn more about actually injecting this using some code inside a control system, I'll get into that in much more detail this afternoon about how to actually accomplish this. And again, very simple change. All I have to do is go to this one parameter and a whole bunch of things, and I can cause this big problem. The next, behold, I am the king. For a very particular control system, there is a command you can put in the HMI. Now, the HMI or the graphic, the way that those work is I'm an operator. I got all these screens that are up there, and I don't necessarily look at all the graphics or HMIs at once. I pull it up. Oh, I want to go look at the current, what's going on inside the reactor, pull up the screen, and get the details about that thing. When I pull up that graphic, if that one line, which I have obscured, because if I told you what it is, you could Google it and figure out which system. And I'll explain why. You can Google it in just a minute. But if that is in that graphic, when you pull up that graphic, you just made that station an administrator that can do anything that you want on that entire DCS network. I don't care what Windows says. I don't care any kind of remote access. I don't care what you have done with identity management or anything. That one command, those few lines, just made you an administrator. I can do anything I want. Now, why is it there? That's crazy. Engineers use it all the time to do things to help the process out. It's been out in the wild for a long time. If the vendor were to say, I'm just going to kill this ability in the system, and they implement that in an upgrade of the software, unless it's super carefully planned, chances are they're going to break stuff out in their customer's environment. The reason that you can find this on a Google search is they recently implemented a patch because it wasn't working properly. So again, it's there for a purpose, and it has good function. But in the wrong hands, you can imagine all the bad things that you can do with it. So it's really a thing that has to be managed very carefully. We'll get more about how to remediate this stuff here towards the end of the presentation. Code invaders. By far, the most dominant thing used to create and manage graphics in the OT world today is HTML. You go to really, really old stuff, and it's really proprietary, but the vast majority of newer HMIs, the graphics are based upon HTML. What is it? It's a bunch of non-version free format things inside the control system and on stations that have generally elevated privileges. Maybe not administrator, but they can do a lot of different things. If I know HTML and I know the control system, I can do about anything that I want. So I can change flow controller settings, not a problem at all. Do SQL injections inside of the configuration database, which is the brains behind the operation. No problem. Hover over a corner, get redirected to a porn site. No problem. Easy. Point is that those graphics, again, it's easy to change, and I basically now have a free format code that I can use to do all kinds of things on the control system. This next one, again, take a little bit more explanation, very specific to a particular type of control system. And let me give you a little history on it. So what does this CPU do? It's a controller in this particular case. It takes in data from a lot of different things, and I talked earlier about this control function. It looks at current values. It solves a problem. It issues a command, repeat. Get data, solve, issue a command, repeat, repeat, repeat. That's the basic things of controls. A lot of the configuration and design of control systems is really based upon older technology, and when CPU power was pretty limited, computing power was pretty limited. They haven't necessarily changed the structure of their systems, and so it was designed with that in mind. In this particular case, to address that, there are two parameter settings, we talked about that earlier, called the sample rate and the calculation period. Now, actually, they have different names, but again, if I gave you the parameter names, you could probably figure out who the control system is. The sample rate is how quickly do I get data. So I want to get that process value. Remember that flow controller I'm trying to get to? How often do I get the data? Every half a second, every 1 second, every 3 seconds? For slower processes, remember, the more things I'm doing, the more I can overload the CPU. So for a flow controller, I may have to get data quick, but for level that doesn't change that much, I may get data once every couple of seconds because I want to balance the load on the CPU. The second thing is, how quickly do I solve the problem? So do I want to solve it once every second? Do I want every 2 or 3 seconds, etc.? That's a configuration that I put inside the system. The other thing that happens is in order for controls to work, there's things that talk to each other. So in this particular case, I have a flow indicator that feeds the flow controller that sends a signal back out to another tag that actually controls it. Those settings have to match. So I've got to make sure that tag 1 and tag 2, those two settings match. What happens if they don't? Well, for an individual tag, if I make those things mismatch, say I get the data once every 2 seconds and I solve every half a second, it's going to cause squirrely control. Things will look weird. It's not going to work right. The operator's going to call the control engineer and say, why can't I keep the level steady in that tank? Why is this flow drifting all over the place? Why can't I get this temperature thing to do its job? I'm putting the thing in manual, controlling it myself. It'll manifest itself as control problems. If I do it for a whole bunch of tags, I could have you chasing your tails for weeks trying to figure out what you would think is a production problem. I can promise you that would be the initial thing. But I can do worse. Remember, let's go back to why this thing was originally designed into the control system. It was because, again, the basic design of this is over 20 years old when CPUs were limited. And if I have some of those older CPUs out there, and I line all this up on one controller, and I make it really fast sample rates, and I make it really fast calculation periods, and I make them solve at the same time, I'll crash the CPU. I'll take it down. Now you don't have control. It's an easy thing to change in bulk. I talked about those applications earlier. I can actually use an application to change this in bulk. I could use the graphic in this particular case to change that in bulk across the entire control system. Interesting thing about all of these things that I have mentioned, from the come on baby light my fire, to code invaders, to behold I am the king, to the reverse. Every single one of these, improperly used, has caused a production problem. I can cite a case in many different places where not properly handling the output characteristic, improperly using this particular command, as well as these settings being done, causing production problems. I can't cite these as a security thing where an attacker has understood this and used it as part of an attack, but my point is, for years, these things have been managed under the banner of safety and reliability. We also have to look at these in terms of security now as well, because if we think people aren't going to learn about this thing, I think history has proven otherwise. The last one I'll talk about, this truly is a vulnerability. Yes, hard-coded passwords in control systems are real. The vendor knows about this. It is not fixed. It is being looked at, but they are aware of it. In this particular case, we have taken in the configuration database from dozens of this particular control system from sites all over the world. And in every single case, the following is true. There is a username called System Engineer that has the exact same password hash. So I'll give them credit. They didn't store the password in the database. They hashed the password. But every single username and password is the same if you have that make and model of control system all over the world. And pretty short hash. We can probably take a pretty good guess at what that password is, so it's not a hard thing to crack. My point is, once you know that username and password, you can get into this system anywhere all over the world. You have the username and password. So again, you say, why? Kill it. Get rid of it. Let's go change that thing. I found this thing. I'm going to go in there. I am going to change that. I'm going to change that password. If you do that, I can virtually guarantee if you do that without doing more investigation, you will break something. In the best case scenario, you're going to shut down the process. Why is that? This system ships with functionality in the background from the vendor that uses that account to do things. So at a minimum, the vendor, before they can release this to fix this problem, has to go through and find those dependencies, those background functions that uses that particular user account, and making sure they don't break things. But secondly is, again, that's been in the wild for a long time. So guess what? Engineers use it. They use that as part of their control strategy to grab an application, to do something, to make stuff happen. So you can't just, and this is the big problem in OT, and all these things I've talked about, there's not going to be a patch. They're not going to come out and fix this thing. This will get this is getting worked on. I do know that. Default passwords is a really bad thing. This truly is a vulnerability. But for many of these other things, you can't just run off and I'm going to go fix it, because the implications of fixing it causes the thing you're trying to avoid, which is production outage or even equipment damage or even worse, release of product. Okay. So I've talked about this. I've said these are problems. Control engineers know these things. They deal with it on a day-to-day basis. They try and manage it the best they can because it has bitten them in the rear end. It's caused production problems. So what do? You've got a problem. I got to do something about it. The end of the day, as I mentioned, patch isn't coming. These are characteristics of the system. You have to deal with it. So the only thing you can do is manage the configuration to make sure you know what is in there and only the changes you want are taking place inside of there. If someone tells you that I can bring you a technology that will not only know every single change to the configuration, but whether it's good or bad, run and hide. You can use technology to identify change, but it is impossible to identify all changes as either malicious or intentional. The only way you can do that is to have a good management of change process that identifies the changes as part of a good workflow and identify changes that are not part of the normal work process. But that comes with cost. It does take effort for people to review this and make this. You're essentially implementing a more rigorous process of managing change on the control system than you had in the past, and you have to be ready to do that. So it's critical to use a risk-based approach to determine where am I going to do this and how much rigor am I going to do on it on my most critical assets. For the industries that we serve, companies already know their critical processes that relates to economics and their critical processes that can kill people. They know that. It's well documented. So those things that are most critical to the business with the biggest safety impact get more management than systems that are less. The other thing, though, is we can do a lot better as a security community. We have not issued good guidance to end-owner operators on how to do good configuration management on OT devices, how to take a risk-based approach, and how to implement all of this. So there's a lot more that we can do inside of there as well. The former SANS Top 20, better practices for configuration that are both risk-based as well as control system specific, because again, you almost need a little manual for each type of control system because those things in there that can get you are different from each vendor. There is an added benefit. Improving configuration management and better understanding this stuff not only reduces cyber risk, it also improves safety and reliability. Because again, all of these things have caused production problems. So, in summary, control systems are weird. They are different. And the way you program these things is different than the IT world. The impact of getting it wrong is big. In the best case scenario, I shut it down or I make bad product. In the worst case scenario, and I know of some of these things, there is a fire and helicopters running around and you're in the news, or even worse, people get hurt. And so managing these assets is critical to improving safety, reliability, as well as security. I got a couple minutes left. Any questions or thoughts? Challenges? Yes, sir. Hold on, they're going to bring you a mic because I think they want to record it, so give me just a second.
Sure, and this is a noob question. I'm very new to ICS security in some ways. Can you explain a little bit more about tags? And I got the general idea of what that attack was doing, but maybe if you could more concisely and clearly define those terms for me, I think that would be useful.
Yep. I'll go back to this. A tag is essentially a control function. And so basically what I do is I have a flow controller tag of a certain type. All right? I'm trying to control flow going into this vessel, whatever it happens to be. And think of it as basically compiled code you get shipped with the product, and I have flow controller type 1, 2, 3, 4, 5 tag, and this controller type is good for level, and this controller type is good for gas versus a liquid or something else like that. And then you configure the tag. You put in things that are like, okay, this tag is going to flow, it's going to control this process. So what am I measuring? Well, I'm measuring gallons per hour or gallons per minute. And what are the ranges that I'm going to operate in. Well, it's going to operate from 0 to 100 gallons per minute. When do I want to alarm the operator? These are all the things called tags that you don't program inside of there. Once you get it from the vendor, you configure it with your specific information to help control your specific process. And that configuration is essentially what determines the logic or the brains that actually makes that particular thing work. And so there's a flow indicator tag takes the field device from the information and feeds the flow controller tag that then feeds an output tag, and that entire loop is what controls your process. And these are individual elements that you have to configure inside the control system. Did I answer your question? And by the way, if you want to get into the nitty-gritty detail, I'll be at the Cabana session, and I can show you this stuff and what they actually look like and get into the detail. So I'm happy to do a lot more about that if you'd like.
Any other questions?
Hi. Same slide. I was wondering how much of the programming part is, because mostly of what we commented now has to do with configuration, and you show lots of configuration issues and stuff. I'm interested in how much vulnerabilities there might be in the domain-specific languages that are used to program these devices. I'm not talking about how to configure their parameters. I'm talking about programming their automation, for example. Let's say, I don't know, a conveyor belt. No, let's say something more complex. A driller, right? That has several PLCs that have to move, that have to activate several motors. Maybe there is something beyond just simple configuration to make these parts moving. And I'm wondering if you have something to share about more complex, beyond configuration.
Yeah, so let me make sure I understand the question. So you mentioned PLCs in specific. If you remember earlier, most of the time when you change configuration of PLC, you take the current configuration program, you put it into some software that the vendor provides, so Allen Bradley and Siemens, et cetera, and you make a change there, all right? Yeah. And you use a language that you're familiar with. Yeah. And by the way, typically speaking in those programs, I can write the code in IEC language or ladder logic or whatever, and then it spits out the thing that goes into the PLC. It's always the same format, which is basically binary.
Exactly.
Right?
Yes, exactly.
And so that programming language that comes from the vendor is the thing that creates the configuration that makes the PLC give us its brains to do its job, right?
Right.
And so are you asking specifically, are there vulnerabilities in that configuration software that I need to be aware of? Is that the question?
More issues at the language level. What the vendor provides you as a high-level language to write your configuration that are later on.
Okay. Yeah. So great question. So there's a couple different things that happen there, okay? The configurator program before it goes into PLC, you can actually choose how you want to program it. So I can use, there's an IEC 62553, there's ladder logic, there's different things in here, and oftentimes I can program it the same in the same software, or sometimes I have to pick the software version, right? The PLC has no idea which language you picked. It has no clue. So you run it through that software, and it basically comes out of that software into essentially a binary program that goes inside the PLC, right? So that's what happens there. You don't do that in the DCS world, actually. You actually do it online. You don't go through a intermediate program. You make the changes directly online to do that. All right. DCS is different. Is a different animal for the most part. Okay. So to answer your question, have there been published vulnerabilities on the configuration software that downloads into a PLC? Yes. But generally speaking, it's easy to discover because it's sitting on a Windows box. It's software on a Windows box. It's a vulnerability. It's easy to patch because you're not going to mess stuff up. Right. So when there's a vulnerability there, not as concerned. I'm more concerned about vulnerabilities in the PLC and the DCS CPUs than in the programming software because, I won't name a vendor, but so-and-so vendor has said there's a vulnerability in that programming software, you upgrade it in 2 minutes, and there's no way you can impact the actual process itself. It's the vulnerabilities at the PLC level and the DCS level that I'm more concerned about because, again, those specific cases that I went through, just quote, upgrading or getting rid of it will cause problems. All right. Did I answer? I hope I answered your question. If not, again, happy to talk live and the Cabanas.
Yeah, thank you.
All right, is that it with questions?
Very good. Thank you all very much. Appreciate it.